everybody's really close to this.
Yeah.
It goes really fast sometimes. I trust you. I've seen it run. Just in case.
Yeah, got it.
You're closest.
Yeah.
Where's the green dot?
Oh.
It's right here, right now.
Sorry.
Just for Sawyer, so it's possible that it's not totally level. Because it usually very
The
easily
sticker
stops
is
right
like
there.
sticking out, so it
Yeah.
pushes the ball.
But that's where the goal is.
Yeah.
That's what I know. That works.
So the point of our project was to solve this labyrinth. So wherever the white ball is the starting point, and wherever we move this green sticker is the ending point. And so it can solve it any way. We'll move it around a little later to show you guys. There are a couple of different elements of the project that we're all going to briefly talk about. What we first did was make the actual maze. So it's just sheets of wood that were laser cut and then stacked on top of each other. And we also had to make a Sawyer gripper attachment because this one doesn't use a traditional gripper. And then painted it colors for the computer vision.
And for the computer vision part, as you can see, the labyrinth got different color. The wall on the labyrinth is blue, and these are all because we want to use the color to tell the different objects, and we feed back the image of the labyrinth and the position of the ball and the sticker for the rough calculation, and the part that Michael worked on it.
Okay. So, first thing you got to do to get from place A to point B is you got to solve the maze. So, there's a node that we made that solves the maze. It uses it's kind of a systematic version of an RRT approach, which we can go into detail later about. But essentially what it does is it first makes a global path from wherever the ball's first position is, and then it's able to detect where the ending point is from the computer vision team, and that's where the global path is. And then as the game starts and in game time, there's a local path created that goes from the ball to the next point on the global path, so it tries to stick to the global path as much as possible. With this information, so it's also important to know that the maze is kind of grid-based. So this is like a 7x7 grid-based maze. That means there's 7 points. It's a 7x7 grid, and with that grid, we're able to determine how far the ball has to travel to go to the next node. That distance, or that arrow vector that it has to travel, is what I sent to William, who is in charge of the robot joint position node, which would actually move the maze based on the direction that I sent it to him from the maze on.
So the way we manipulate the labyrinth is to orient Sawyer's arm in such a way so by tilting one angle of the arm, the ball would just roll in one direction, and tilting the other joint to roll the ball in another direction. And to control the joints, we use both position and velocity control that came with the Intera SDK. And yeah, that's
So one thing we forgot to say is actually CV part has only one node, and there are 2 services and one topic connecting to the maze solving part, and 2 services is used to for the maze solving part to call the service at the beginning to get the endpoint and the beginning point, and the topic stuff keep publishing the ball point at the current time. So this way.
we can't just drop the ball anywhere.
And
Just start again.
And one thing that is noticeable is that, so when it does turns like where it is now, when it hits a wall and then turns, it's pretty easy, but when it has to go into a slot like this, where there's no walls around either side, it has to sort of swing in. And so it has trouble with that, as you can see now. But it does eventually get it.
Did it first try last time?
Yeah.
If any of you want to see, the global path should be plotted on room 2.
yeah.
Oh, that's awesome.
This is based from where it started initially when we started.
It's currently having exactly the same trouble I would have.
Because of the
There we go.
refresh of the image will slow down.
That computer vision is so clean.
Should I move?
Yeah, I know.
Look how well they're
It happened first try.
I know.
Man.
And the reason why we don't use this one is because the resolution.
So
That's better resolution, right? I can tell from the camera. I was like,
So right now we're gonna switch the endpoint and try to solve it.
like that.
Oh, I used
that
camera.
It's for what camera is it? What is it? It's like a camera too.
What's that? Is that the
What's that?
Yeah.
That's how we roll.
That's just regular.
Oh, just regular?
Yeah, it's just regular. You can, when they're running it, you can actually see the computer vision.
Yeah, I saw it. It's pressing it.
Yeah, so we didn't use the Sawyer camera. We used
Because it's like,
So you just use different goal and you can stick it.
yeah. So we used to rerun, relaunch. Yeah.
Rerun the path.
Yeah.
So you refresh it each time.
So it's rebuilding the whole maze. It has no prior knowledge of the maze.
So could you put in a wall in the maze then? Like you could switch a wall somewhere else.
Yeah.
So if you made like a modular maze.
Yeah. We actually made it modular so that the base is connected to the gripper, and then the maze can come off and on, and there's like 2 screws, so you could put a different maze on.
I saw some circular.
Yeah, I started making a circular maze.
Yeah, there is some code implemented that would work on the circular maze.
oh yeah, that would have been cool.
Yeah, but we didn't really.
Right.
The control part's a lot harder than the circle.
Yeah.